Okay, so we substitute those expressions that we just saw into the ordinary differential equation, and so we have assembled those expansions here. So this first group of terms here is the expansion for z squared times y double prime, which you may see from a previous expression. The second term here is the second term that we have, which is z times, remember we put z times pz, for which we had an expansion, which is this little thing here, and then the expansion for y prime is the rest of it, and then this is the third term of the differential equation, which is in this form. And so here we have the full differential equation in all its glory, and it may look sort of algebraically tedious, but it's all logical. We just have to laboriously write down each term, and there is no magic that is going to go on. It's very transparent. We just have to systematically write all the terms, and the consequences would follow. All right. So we can now look at each of these expressions and ask if this whole sum has to be equal to 0, then and if this whole sum is equal to 0 for any value of z, then the only way that can be true is that the coefficient of each power of z must vanish, and then this equation would be valid. And so we look for the coefficient of the lowest power here, and so the lowest power is when k is equal to 0. So that is z to the r. Of course, here the way the equation is nicely written is that here z to the power r plus k and z to the r plus k and z to the r plus k is commonly present in all the terms, and so therefore we can collect these coefficients in a simple way. So we take this, we copy it here, but since we want to have the lowest power here that is associated with k being equal to 0, that k equal to 0 we want to substitute in here, and so this coefficient here is copied here. P0 from here shows in here because we want to have the lowest power here, and the lowest power will come when p, this expression has n equal to 0, and so that's why p equal to 0. And similarly, to have the lowest exponent, we have q0. And so this whole thing multiplies ak times z to the r plus k, where k is equal to 0, or this is an exponent of z to the r. And we want that to give non-trivial solution, meaning this coefficient here, a sub 0, we don't want that to be 0, and therefore this quantity in this curly bracket must be equal to 0. So if we collect these terms here, we would see that the coefficient in front of this is r minus 1 from here, r minus 1, k is equal to 0 here, and this is 0, so that's just r, and here k is 0, so it's r times p0, and q0 is simply q0. So sum of this must be equal to 0. So this requirement that the coefficient of z to the r does not vanish, when coefficient vanishes so that a sub 0 is not 0, that equation is called the indicial equation. And so we can work with this equation, we can rearrange it and solve it, and so that is what we're going to do next. So we simply rewrite it, and we have this quadratic equation, and r square plus p0 minus 1 times r plus q0 is equal to 0. So this quadratic equation has two roots, and we can now discuss the various cases that would follow. So we have this quadratic equation, which is the indicial equation, and we can solve it to get the two roots, to get the exponents. And so as we write those two roots, we have a number of cases to discuss. And so the simplest case arises when these roots are distinct and real, and let's order them such that the root r1 is bigger than the root r2. And if the difference between the bigger root r1 and the smaller root r2 is not an integer, then we have the simplest situation, and the power laws z to the r1 and z to the r2 give us two linearly independent solutions, and the associated power series expansion that we have suggested would define a complete solution to the problem. And this situation is commonly encountered, but we have other cases to discuss also. So the next case that is logically more easier to describe of these other cases here is when the two roots are real but they are equal, the case of a double root which is real valued, in which case z to the r is one of the roots, and the other root, other behavior solution to the other homogeneous solution would be given by z to the r times log of r. And so this we had encountered previously in the context of Euler equation, and this is an equation which is locally becoming an Euler equation. And so the final case that is remaining here is when we have distinct real roots, but the difference between the two roots is an integer. In this case, what we have is we have something in between these two cases. We have the root r2, z to the r2 is a linearly independent solution, but for the root r1, which is an integer, r2 plus an integer, we have to go through the method of variation of constants to determine the other solution, and that will correspond to having a solution which involves a logarithm of z as well. Finally, the case with complex roots is one where there is no simple power law solution, because we are talking about power law solution with a complex root, and so as we have seen in the context of Euler equation, that is not a power series anymore, and so we don't have this type of behavior when we get complex roots. So now we have determined the unknown exponent, and so we are now ready to substitute that value of r in the equation that we had with the differential equation, which involved all these coefficients a sub k's. And so at each order of the exponent, we then have an equation which can be solved. So we can take, for example, a0 equals 1, and then we can find all the other values of a1, a2, a3, and so on in terms of a0 equals 1, or we can factor a0 outside completely. And so these recurrence relations then provide solution in terms of a0. And reason there is a constant factor that will multiply the complete homogeneous solution is because it's a homogeneous equation, and so any multiple, any constant times that solution is also a solution. And so we want to note that famous ordinary differential equations that we have encountered before, such as the Bessel's equation, or the Legendre equation, or the Chebyshev equation, or the Airy equation, or a broad class of equations which are called hypergeometric equations. Special cases of hypergeometric equations become these particular equations that we have referred to before. They are all of the form that we have talked about, and this method that we have just described, called the Frobenius method, allows us to find behavior of these solutions. These equations, they all have regular singular points, and so this method applies, and we can find series expansion solutions for all of these cases and so on. And we, for example, had illustrated the behavior of Bessel functions. That behavior can be found by going through this process for Bessel's equation, and one can analytically establish that that is the nature of the solution. And so Frobenius method is a very powerful method. It's algebraically a little bit involved. You have to write a number of expansions and check that you don't make algebraic mistakes in the substitution, but it provides a very powerful way of finding the nature of the solution.